Hello everyone, my name is Honorable Sadrin Anna Henry, and today I will be presenting our assignment for BLK 2383 Power System Technology. The title of our assignment is Per Unit Modeling and Analysis of a Multi-Voltage 3-Phase Power Network. In this presentation, I will explain how we develop a complete per unit model of a power system consisting of a generator, transformers, transmission line, and an industrial load using a common base system. Before we begin, I would like to introduce our group member. The members involved in this assignment is Honorable Sadrin Anna Henry, me, Honorable Ryan Anna Gilbert, and Khairul Idham bin Sam'ah. To begin, let's briefly discuss the per unit system. The per unit system is a method used in power system analysis to simplify calculation by expressing electrical quantities relative to the selected base value. Instead of using actual value such as volt, ampere, and ohms, the values are converted into dimensionless per unit values. This approach is especially useful in multi-voltage network because it eliminates the need for repeated conversion across transformer voltage level. For this assignment, the per unit system is applied to a 3-power network containing a generator, 2 transformers, a transmission line, and an industrial load. The final model can later be used for load flow and fault analysis. The objective of this assignment is to develop a complete per unit model of the given power network. To achieve this, all system components must be converted to a common base of 100 MVA and 13.8 kV. Because the system operates at different voltage level, a common reference is required to ensure that all components can be analyzed consistently. Once the conversion is complete, the entire network can be represented using an unified per unit model. Let's look at the data provided for the system component. Generator G1 is rated at 50 MVA and 13.8 kV with a reactance of J0.20 per unit. Transformer T1 is rated at 60 MVA with a voltage ratio of 13.8 kV to 132 kV and a reactance of J0.10 per unit. The transmission line operates at 132 kV and has an impedance of J40 ohms. Transformer T2 is rated at 40 MVA with a voltage ratio of 132 kV to 33 kV and a reactance of J0.08 per unit. Finally, the industrial load is rated at 30 MVA, operating at 33 kV with a leaking power factor of 0.85. The common system base selected for the analysis is 100 MVA, while the generator side base voltage is 13.8 kV. Now let's look at the overall power system configuration. The system begins with generator G1 producing electrical power at 13.8 kV. The voltage is then stepped up by transformer T1 to 132 kV for efficient long distance transmission. The power is transmitted to the transmission line before reaching transformer T2. Transformer T2 reduce the voltage from 132 kV to 33 kV, which is then supplied to the industrial load. This singular diagram provides a simplified representation of the entire power network and forms the basis for our per unit analysis. For performing the per unit calculation, the network is divided into 3 voltage zones. Zone 1 includes the generator and the low voltage side of transformer T1 with a base voltage of 13.8 kV. Zone 2 covers the transmission system between transformer T1 and T2 operating at a base voltage of 132 kV. Zone 3 includes the secondary side of transformer T2 and the industrial load with a base voltage of 33 kV. The voltage zone are determined by the transformer voltage ratio, which establish the base voltage for each section of the network. This step is important because it ensures that all subsequent per unit calculations are performed accurately and consistently.
Alright, so today I will be making you through the process of determining base quantities for per unit analysis. So we will be referencing the data present in this slide, which illustrates the systematic approach to selecting and calculating these values. First of all, as shown in the left section, we begin by defining a common base apparent power, which is this example is S base equals to 100 megavolt ampere. So the system is divided into three distinct voltage zones separated by transformers. So determining voltage zones, to find the base voltage V base for each zone, we apply the transformers ratios. Starting in zone 1, our base voltage is 13.8 kV. Applying the T1 ratio of 13.8 over 132, we determine that V base zone 2 is 132 kV. Finally, applying the T2 ratio of 132 over 33, we find that V base zone 3 is 33 kV. So once we have established the base voltage, we calculate the remaining base quantities using the formulas outlined in this slide. So first of all, base current, the formula is S base over square root 3 times V base. So the base impedance equals to V base power of 2 over S base. So by reviewing the result, the table on the right side summarize this result, which is zone 1 equals to operates at 13.8 kV, resulting in a base current of 4183.7 ampere and a base impedance of 1.9044 ohm. For zone 2 is operates at 132 kV, resulting in base current of 437.4 ampere and a base impedance of 174.24 ohm. And zone 3 is operates at 33 kV, resulting in a base current of 1749.6 ampere and a base impedance of 10.89 ohm. So by establishing these base values, we create the necessary foundation to perform per unit analysis across the entire system. So this image illustrates how to perform a change of base for per unit impedance values in power system analysis. Equipment is often rated on its own specific base, but we need to convert everything to a common system base to perform accurate calculation. So the conversion formula, to change the per unit impedance from an all base to a new base, we use the following formula, which is X new equals to X all times S base new over S base all times V base all over V base new in the power of 2. So breakdown of this example for generator 1, which is G1, X equals to 0.2 per unit at 50 megawatt ampere and 13.8 kilovolt. So we scale the impedance by the ratio of the megawatt ampere bases. Since the voltage remains 13.8 kilowatt, the voltage ratio is 1. So X generator 1 equals to 0.2 times 100 over 50 times 13.8 over 13.8 power of 2, and then the answer is 0.4 per unit. So for transformer T1, X equals to 0.1 per unit at 60 megawatt ampere and 13.8 kilowatt. The calculation. So for X transformer 1 equals to 0.1 times 100 over 60 times 13.8 over 13.8 equal to 2, and then the answer is 0.167 per unit. So to continue our analysis of per unit conversion, we look at the transmission line and transformer T2 as detailed in this slide. So for transmission line, in zone 2, the per unit impedance is calculated by dividing the actual impedance of 40 ohm by the zone 2 base impedance of 174.24 ohm, resulting in 0.2296 per unit. For transformer T2, to cover transformer impedance to common 100 megawatt ampere base, we apply the conversion formula to the given 0.08 per unit value, which will a final value of 0.2 per unit. So finally, we address the load impedance calculation as illustrated in this slide. To find the per unit load impedance, we first normalize the load's apparent power to the 100 megawatt ampere system base and determine the power factor angle. By using the formula ZL equals to V square over S, where V equals to 1 per unit for nominal conditions, we calculate the polar form of the impedance 3.333 and 31.79 angle per unit and convert it to rectangular form, resulting in reveal part of 2.833 and relative part of 1.755. So to complete our analysis, we consolidate all the calculated per unit impedance values into an equivalent per unit diagram as shown in this slide. So the final series reactance values used to model the system are as follows: G1 equals to 0.4, T1 equals to 0.1667, transmission line is 0.2296, T2 equals to 0.2, and load is 2.833 plus 1.755. That's all from me. Thank you.
My name is Rudy Ryan. Today I'm gonna present about per unit result metric. Based on this slide, everything is now on the same 100 megavolt amp base, so we can put them all on one vector diagram. You can see in the metric that generator G1 went from J0.20 on its own 50 megavolt ampere base to J0.40 on the new system base. Transformer T1, which was J0.10 on a 60 megavolt amp base, is now J0.1667. The transmission line, originally given in ohms, is now J0.2296 per unit, and transformer T2 is now J0.20. The industrial load remained at 2.833 plus J1.755 per unit because it was already in per unit. So with this new value, we have a unified system ready for analysis. So why do we actually use per unit? First, it makes calculation way easier in system with multiple voltage because you don't have to keep shifting impedance back and forth across transformer. It also takes huge ugly numbers like thousands of amps and shrink them down to something small and simple, like around 1 per unit. This let us directly compare different pieces of equipment like a generator and a transformer. Even if they are totally different size, on top of that, the ideal transformer completely disappears from our circuit model, which saves us a ton of work. It also gives us a clear picture of system health. Since 1 per unit means normal voltage, we can spot a dip or a spike right away just by looking at the number. And finally, this is the language that all the big commercial software package speak. So learning it gets us ready for real world load flow, and at our result, we can see some clear takeaway. Generator G1 has a reactance of 0.40 per unit, which is much higher than T1, 0.1667, meaning the generator will cause a big voltage drop when the system is under stress. The transmission lines sit at 0.2296 per unit, which is pretty high for a 132 kilovolt line. So it's likely a long line, and that will really affect how stable the system stays during disturbance. Between the two transformers, T2 has a higher reactance than T1, 0.20 versus 0.1667, simply because transformer 2 is physically smaller at 40 megavolt amp compared to T1 60 megavolt amp. Finally, the load has a resistance of 2.833 per unit, which is actually quite low. So that tells us it's drawing a large amount of current with a 0.85 lagging power factor, confirming it's a heavy industrial type load. To wrap it up, we successfully built a complete per unit model for this 3-phase power network. We identified all the different voltage zones, set up the right base value for each, and converted every component impedance onto one common 100 megavolt amp base. Now that everything is normalized and consistent, it makes our calculation much simpler and cleaner. More importantly, this model is now fully ready to be used for real advanced studies like load flow analysis and short circuit fault calculation.